Hello everyone, and welcome back to this discussion and exploration of elementary probability and statistics. Today we're going to be continuing our journey through the realm of elementary probability theory, in particular discrete random variables and their associated probability mass functions. Today we're going to be taking a closer look at two special discrete probability mass functions, in particular the geometric and the negative binomial PMFs. So let's just review a couple things that we need. So a trial is said to be binary. Some people also use the word Bernoulli if it only has two possible outcomes. The most common structures for binary trials are usually true-false, success-failure, heads-tails like flipping a coin, and 0-1, but obviously there are other ways you could partition a space into two sets, for example, a set and its complement, for example, happy versus not happy. And also, we say x1 and x2 random variables are independent, provided that the conditional probability x2 given x1 has already occurred is just equal to the probability of x2. That is, x2 doesn't really care about x1. So now let's introduce the geometric random variable. So what x is going to represent here is the number of independent binary trials until the first and only success occurs. If x represents something that is pretty much parallel or equal to this type of structure, then x is called a geometric random variable. Before we get into the actual real-world applications of geometric distributions, I just want to go over a couple basic theoretical things that we definitely need to know to solve problems with this structure. So let's assume that we have x, and x is going to be a value. Now keep in mind, how many trials do we need minimally until we get a first and only success? Well, obviously the minimum value that x could be is 1, because we need at least one trial for us to have at least one success. So when x is equal to 1, let's also assume, let the probability of success be equal to lowercase letter p. So what is the probability that x is equal to 1? Well, the probability that x is equal to 1, which I'm going to denote in probability mass function form px of 1, this is going to be equal to the probability of getting our first and only success on trial 1, which is just going to be equal to p. Now, if we go to x is equal to 2, that means on trial 2, that is our first and only success. So the probability that x is equal to 2, or equivalently px of 2, will be equal to the probability that our first trial was a failure and the second trial was a success. So since they are independent, I can just do the probability of failure on the first times the probability of success on the second, which is just going to be 1 minus p since they're complements times p. Similarly speaking, I can go to trial number 3. So if we're on x is equal to 3, that means the first two trials were failures. So we can say that the probability x is equal to 3, or equivalently px of 3, will be equal to the probability of failure on the first and failure on the second and success on the third, which is just going to be equal to the probability of failure 1 times the probability of failure 2 times the probability of success 3. And they're all independent, which means the probability of failures and successes are the same regardless of the trial. So that means this is going to be equal to 1 minus p times 1 minus p times p, or in simple form, 1 minus p to the power of 2 times p to the power of 1. So that's going to be what px of 3 is equal to. And obviously you should be able to start to see a pattern here. So let's see if we can just generalize this to the general case. So the probability that x is equal to little x will be equal to 1 minus p to little x minus 1 times p. Right? And keep in mind, this is the probability that capital X is equal to little x. Right? And this structure has a name. This is called the geometric probability mass function. Right? So a couple of very important things that you definitely should notice. The little value x can only be in the interval 1, 2, 3, and 4, and it will go up to infinity because it could take at least 5 million tries, highly unlikely, until we get our first success. And the graph of a probability mass function that is geometric will be monotonically decreasing, because p and 1 minus p are numbers between 0 and 1. So when we multiply by a number between 0 and 1, it makes the value smaller. So what you're actually going to see is a graph that has this type of shape. In particular, this is a geometrically decreasing distribution, right? And that's going to be equal to p. Right? And let's actually just write that. So this is exponentially decreasing. Right? So it's an exponentially decreasing function, and the domain in particular is not bounded above. That is, if I asked you what is the probability that x is bigger than 5, you would have to do 6, 7, 8, 9, 10, 11, all the way up through infinity. Right? So now that we have a probability mass function, now it pretty much goes back into the old world. How would you find, for example, the expected value, the variance, the standard deviation of this random variable x? Right, so let's formally state this question. So if x is geometric, then what is the expected value of x? Which some people also write the mean of random variable x. So we already know how to find expected values for arbitrary probability mass functions and discrete random variables. So remember that if p x of x is equal to 1 minus p to the x minus 1 times p, for x belonging to the interval 1, 2, 3, and so on, then the expected value of x, by definition, will be the sum across all values of x times px of x, right? And keep in mind, this is always true for all discrete random variables x. And for our geometric case, this is going to be equal to the sum from x is equal to 1 to infinity of x times 1 minus p to the x minus 1 times p. And this is for geometric random variables, right? Now, obviously, this is the answer, but it's not very manageable. Obviously, you would have to do some fancy math to get this equal to a nice expression. And actually, what you get is just 1 over p. Isn't that nice? So that complicated-looking mathematical expression actually just turns into 1 over p. And similarly, if you find ex squared, which keep in mind is the sum across all values of x squared, times p of x, we're actually going to get, for the geometric random variable, is 2 minus p over p squared. Right? So that also turns into a nice mathematical expression. And again, if you're only caring about the applications, then just knowing that the expected value in the second moment of a geometric random variable having these formulas is all you really need to know. And if you're on the theoretical side of probability, then definitely use whatever fancy tricks you have for infinite series and convergence that you may know. For example, geometric series. You also have some derivatives, since there's a little power rule expression here and so on, right? So it depends on you and what you're kind of into. Regardless, if we have the second moment and the mean, then we should be able to find the variance of this random variable, because this is always equal to the second moment minus the mean squared. Right, and keep in mind this is always true for any discrete and also continuous random variable. So for us, this is going to be equal to 2 minus p over p squared, and then minus 1 over p, the quantity squared, right? So this is true only, or potentially only, geometric random variables. They have the same exact denominator, p squared and p squared, so we can just subtract the numerators. So we're going to have 2 minus p minus 1 over p squared, which is just going to be equal to 2 minus 1 is 1, and then we're going to have 1 minus p over p squared. This is the variance of the geometric random variable. Therefore, if I ask you what is the standard deviation of x, which we sometimes abbreviate by sigma x, this will just be equal to the square root of 1 minus p, all divided by p. Right? And some people also abbreviate the variance as sigma x squared as well. Right? So those are how you find the expected value and the variance and standard deviation of geometric random variables without having to do any fancy math. So let us summarize this. So if x is geometric, what are the only formulas that you in some sense need to know? So the probability mass function for geometric random variables came out to 1 minus p to the x minus 1 times p. And this is only true for x is equal to 1, 2, 3, up to infinity. The mean of this random variable came out to 1 over p. And the standard deviation of this random variable came out to the square root of 1 minus p divided by p. Now that we have the important theoretical aspects of the geometric variable discussed, now let's do a real-life example on how this can be used in practice. So let's suppose you go to the gym occasionally, and when you go, you do not have a productive workout 13% of the time, with each visit independent of another. What is the expected number of visits until your first unproductive workout? So a couple of things that I really want to emphasize here. So when you go to the gym, you do not have a productive workout 13% of the time. What is the expected number of visits until your first unproductive workout? Notice that these items match each other in context. So what I'm going to do is I'm going to let x be the number of visits until your first unproductive workout. So therefore, the probability of success here, where success is equal to unproductive workouts, so the probability of success is equal to 13%. And also, all trials are independent, because pretty much that's what it says here. And if it's not, usually we assume so and accept the consequences if that assumption is not met. Or you can build conditional probability mass functions, which are a little bit more advanced, which we'll get into another time. Right? So here we have x is the number of trials until your first quote-unquote success occurs. The probability of success is 13, and all trials are independent. So by definition, since x is a sequence of trials until your first and only success occurs and all the trials are independent, we have that x is geometric. So since x is geometric, we have a formula for the expected value that's just going to be equal to 1 over p, and p is equal to 13%, so we have 1 divided by 13%, which is approximately equal to 7.6923. So we expect somewhere between 7 and 8 visits until we get our first unproductive workout. So if you get your first unproductive workout on trial number 2, that's highly unlikely. And if you get your first unproductive workout somewhere around trial number 50, that's highly likely for you, assuming that your goal is not to have an unproductive workout. Right? So now we have identified x to be a geometric random variable, so we have the expected value. You could also get the standard deviation if you want. But let's do some probability examples. So what is the probability you do not have an unproductive workout until visit number 5? Right? So our first quote-unquote success, right, so that's going to be a success, doesn't occur until number 5. So that means what? So that means what we want is going to be failure, 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 and success, right? Because that's trial 1, 2, 3, 4, and 5 success. So from the perspective of probability mass functions, that's going to be px5, which is going to be 1 minus p to the power of 4 times p to the power of 1, which for our example is going to be 1 minus 0.13 to the power of 4 times 0.13. And once you work out that numbers, that's going to be approximately equal to 0.745. Let's do one other example that you could encounter. What is the probability you do not have an unproductive workout until when do we want to go to? Let's go until at least visit number 3. So we want the probability of at least 3 for x. So that means we want the probability of at least FFS, that's trial 3, or FFFS, right, that's trial 4, or FFFFS, that's trial 5, and so on. So technically speaking, that's the probability that x is greater than or equal to 3. In probability mass function form, that's going to be equal to the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 5. But keep in mind, geometric random variables are not bounded above, but they are bounded below. So we can actually look at the complement, because notice that the only things we're missing in the sequence is x is equal to 1 and x is equal to 2. So this is going to be equal to 1 minus its complement, so the probability that x is less than 3, which is going to be 1 minus the probability that x is equal to 1, plus the probability that x is equal to 2. So once you actually figure that out, what's that going to be? So this is going to be equal to, in general form, the probability of success on trial 1, and then the probability of failure, and then success on trial 2, which is going to turn out to 1 minus p times p. And then once you work out those numbers, that's going to be approximately equal to 7569, so about 76%. So that's how you can use the geometric random variable in the general context and in a practical context as well. But keep in mind, geometric random variables only apply to scenarios where you kind of have to wait until you get your first and only success. So if you want more than one success, then you cannot use the geometric random variable. But there is one distribution, in particular the negative binomial distribution, that will accommodate more than one success for you. Now let x represent the number of independent binary trials until the rth and last success occurs. Then x is going to be called a negative binomial random variable. So instead of x being the number of trials until the first and last success, now we're going to be allowing ourselves to have more than one success. And once we get that rth success, then we're going to terminate our sequence. So as a guiding example, let's assume that we want 3 successes. That is, r is equal to 3. That means 3 successes are going to be staggered across the sequence, with the third on the last trial and the other 2 on any of the trials before. So if somebody asks you, what is the probability that x is equal to 3? Well, what are the possibilities that x can be? Well, it's clear that if r is equal to 3, that means x must be greater than or equal to 3 for this to be possible, right? Which means the probability that x is 1 and the probability that x is 2, both of these are equal to 0. And why is that? Well, we need at least 3 trials to have at least 3 successes, so x has to be at least 3 for this to even happen. So what about the probability that x is equal to 3? Well, we want 3 successes in 3 trials, which means this is the probability of getting success, success, and success, which is just going to be equal to p cubed. That's pretty easy. But what about the probability that x is equal to 4? So this is going to be equal to the probability. So if we have 4 trials with 3 successes, the last of them being a success, that means we're going to have 1 failure that's going to be scattered in the sequence somewhere. So we could have, for example, success, success, failure, success, or we could have success, failure, success, success, or we could have failure, success, success, and success. These are the only 3 combinations that you could have. And keep in mind, why is this last one not having a failure? Because that is our third and last success in our sequence, right? So the only things that are rearranging are the 4 minus 1 trials in this sequence. So we're pretty much just looking at the rearrangements of SSF in that set of 3. So what would that be equal to? So that's going to be equal to 3 choose 2, right? So we're going to be rearranging. So this is going to be 3 trials, 2 successes being rearranged in that sequence. And keep in mind, what's so special about 3? Well, that's just going to be the number of trials, 4 minus 1. And what's 2? Well, that's obviously going to be r is equal to 3 minus 1 as well, because the last one's not being rearranged, so we'll just be left with 2. And then what are we going to have? Well, we're going to have 3 successes and 1 failure, so it's going to be 1 minus p to the power of 1, and then p to the power of 3. So that's what probability of x is equal to 4 is going to be equal to. So you might be able to see a pattern immediately. So if I want to say, what is the probability that x is equal to little x? So this is going to be equal to the probability of, let's say, star, 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 all the way down to star, star, s, and the rearrangements of these, because the last success, which is the rth success, needs to be on the very end, and that means we're going to have r minus 1 successes somewhere in this particular sequence, right? And this is trial number x, and then we're going to have x minus 1 trials located within this mixture. So we have x minus 1 trials, r minus 1 successes that could literally be anywhere in this sequence. Therefore, we know exactly how to calculate that via the perspective of rearrangements. So we're going to have the C. So how many trials are being rearranged? That's going to be x minus 1. How many successes within them? That's going to be r minus 1. Overall, how many successes and failures do we have? So we're going to have our failures, we're going to have our successes. So we're going to have our successes, and since we have x trials, we're going to have x minus our failures in that sequence. So this is going to be our probability mass function, which is known as the negative-binomial probability mass function. And what is the minimum value that x can be? So if we want our trials, that means we need at least, if we want our successes, we need at least r trials. So the smallest value is going to be r, and then r plus 1, and then r plus 2. And again, this is not bounded above. Now there are some formulas for the expected value and variance and standard deviation for negative binomial random variables, but I'll leave those theory people to take care of this for you. So the expected value for negative binomial random variables is actually going to be just a scalar multiple of geometric. So we have r over p, and the variance of x is going to be equal to r times 1 minus p all over p squared. And obviously, if you know the variance, you can easily find the standard deviation as equal to the square root of r 1 minus p all over p. And it's very important to note one special case, that if r is equal to 1, then negative binomial just turns into a geometric random variable. So now that we have the theoretical things of the negative binomial built, and we have a probability mass function, now let's solve some real-life problems with this distribution. Let's suppose that you are in a competition that allows you to get promoted to the next rank if you win 5 rounds, with each round independent of another, and the probability of winning any round is 4.48%. What is the expected number of rounds until you get promoted if you start today? If you want to pause this video and see if you can figure out this answer, feel free to do so. So let's first off figure out what we're working with. So let's assume that a success is winning a round. And therefore the probability of success will be equal to 48%, and we need 5 rounds to get promoted, right? So let r be equal to 5, right? Because if you go to r is equal to 6, we're already promoted from the 5th, so we technically do not need the 6th. So r is equal to 5, the probability of success is 48%, and the trials are independent. Trials are independent, right? So once you get that 5th, you're going to be promoted automatically. So therefore, you should be able to see that x, which is going to be the number of trials or rounds or games until the 5th success, right? And keep in mind, until the 5th success means promoted. Therefore, this is going to be a negative binomial random variable. Negative binomial random variable. So since it's a negative binomial random variable with p is equal to 48% and r is equal to 5, we have a very special formula for that can give us the answer immediately. So this can be r times p, or r over p actually. So r over p, which is going to be equal to 5 divided by 0.48, which will be approximately equal to 10.4167. So the expected number of trials or games you need to play is going to be 10 games, anywhere from 10 to 11, leaning more towards the 10 side. Right? So if you get your 5th win on trial number 5, I mean, that's super, super great. And if you get your 5th win on trial number 500, that's kind of unlucky for you because you should be getting it somewhere between 10 and 11. So let's actually do one more problem. Let's do a probability problem. So what is the probability it takes at most 7 trials until you get promoted with the last trial? Actually, no, we only need to say this until you get promoted. All right, so what do we have? So at most 7 trials until you get promoted. So again, that's still r is equal to 5. So we're allowing ourselves to have at most 2 losses, right? So that's at most 2 losses. Because if 5 of them are wins, then we're allowing for at most 2 of them to be losses in that sequence. So that means what? So we're looking for the probability that x is less than or equal to 7, but the minimum value is going to be 5 because we need at least 5 trials to get 5 successes. So we can actually reformulate this: 5 less than or equal to x less than or equal to 7, because the probability that x is equal to 1, 2, 3, and 4 are already equal to 0, so adding them here won't really get you anywhere. So there's only 3 values that make this true, and that's 5, 6, and 7. So we just need to find 5, find 6, and then find 7, and then add together. So let's actually walk through these calculations just to make sure we understand what we're doing. So our last success is going to be on trial number 5. And we're going to have 5 successes, 0 failures, because we need 5 successes in a sequence of 5. So that means we have 0 failures, 5 successes. And we're going to be rearranging those 4 successes before the last one within those 4 trials. But technically, you know, SSSSS or SSSS rearranged. There's only one rearrangement, so you should be able to see that this coefficient is just going to be equal to 1. So you actually don't really need it. But what's more interesting is the last 2. Right? So when we go trial 6, that means 5 trials are going to be rearranging 4 successes within them. We're going to have 1 failure in that sequence, and we're going to have 5 successes within that sequence of 6. And then for x is equal to 7, then when x is equal to 7, then we're going to have 6 trials that are going to be rearranging, because the 7th is always going to be a success. And since we're going for 7 successes, that means how many trials are going to be permuting within that. Keep in mind, we're still aiming for r is equal to 5. That's not changing here. So you're still going to have 4 trials within that sequence of 6 being rearranged, and then we're going to have 2 failures, and then we're going to have 4 successes there. Actually, no, 5. 5, 5, 5, 5, 5. Right, that's always going to be true. Right, so make sure that these numbers add. So 0 plus 5 is 5, 1 plus 5 is 6, 2 plus 5 is 7. And keep in mind, the bottom is pretty much always going to be the same for you, because keep in mind, we're always going to have r 5, and that's always going to be r minus 1. So that's going to be r minus 1. This is going to be r minus 1. And that's going to be x minus 1, x minus 1, and x minus 1. So once you actually do all of that math out and you do not make any simple mistakes, the probability that it takes you at most 7 trials to get 5 successes, so probably that x is less than or equal to 7, will be approximately 1951 as a decimal, or about 20%. So those are 2 special probability mass functions, geometric and negative binomial, that are used to model the probabilities and distributions of the number of trials until you get your first, second, third, fourth, or rth success in a sequence. There are several other probability mass functions which we will get to in the near future, so I hope to see you there, and I hope you enjoyed this video. Take care.